begin our discussion today with the rational root theorem. And this provides, we're going to provide you really with two tools to add to your tool belt as you learn to factor. I'd like to just eventually, remember the goal here, I'd like to just be able to hand you a 5th-degree polynomial, which we'll do before we leave today. I'm just going to hand you a 5th-degree polynomial. We're just going to try and factor it, like go, right? So we need some more tools in our tool belt. This is one of them that I think will be useful to us. It's called the rational root theorem. Take a minute to study it, consume it, write it down for life, understand it, devour it.
Is this the same as the rational zeros?
Yeah, is that what's called in your book?
Yes.
Okay, well,
I
yes.
didn't know what that was, so I was confused.
Same thing. Yeah. Rational root just has like more alliteration to it, you know. So, rolls off the tongue. Try to apply it to this problem already. It's also, I put the slides online too, if you want.
If he wants fresh coffee. If he wants
New one.
Yeah, I just like what more about the rational root theorem. Yeah, that's the thing.
Not to homework 2, not yet. Is homework 1 not up there? No, I didn't put them up today. All right, so are we ready to actually digest this? Let's see if we can figure out what this says. So what we're saying is that P, if you claim that a rational root, if you claim that a rational number that you own is a root of my polynomial, like say you claim that the root 5/7 or something is a root, well then it should be true that the numbers you just said, 5 and 7, divide the constant term, that is the last, if it's in standard form, the last thing, and the leading coefficient respectively. So 5 should divide the constant term, and 7, if I claim that 5/7 is a root, then 7 should divide the leading coefficient. Okay, that's the claim at least. So I think maybe it's clear already that 5/7 isn't a root of this. But again, this is for rational numbers. If you come to me with some other number, it's not a rational number, then I don't have anything to tell you. But if you claim that something is a rational root, then it should obey what this says. And actually, we are going to work toward a proof of this. I have some challenge problems for you this unit that maybe I'll even hand them out today if we have some time. And in that we'll walk through a little bit of a proof of this, at least the beginnings of a proof of this, and guide you toward a proof of why this might make sense actually. But for now, you can believe me for now at least, okay, that this is true. So give some possible things that might be roots of this. That is rational numbers that pass this test, this filter, for this guy. That is numbers, the numerator of the rational number divides this, -3, and the denominator divides 4. Keep in mind that plus and minus both work here, right? So, yeah, give an example. Just give one example. Yeah.
Plus or minus 3 over 2.
Yeah, plus or minus 3 over 2 is a possible rational root. Right, so the possible rational roots might include plus or minus 3/2, right? Give me another one, Piper. Plus or minus 3/4. Yeah. What else?
plus or minus 1.
plus or minus 1 over 2, because 1 divides into 3 and 2 divides into 4. In fact, just to kind of make our work systematic and make sure we don't miss anything, we could write up here 1 and 3. And over here, what do we have? 1, 2, and 4, just to make sure we get every combination. Any of these things divide by any of these things. So is there anything we're missing? Someone else come along? So what I heard from Shivani. Good. Plus or minus 1 is going to, in fact, always be in the lists we make of this kind. Yeah? Plus or minus 1/4. We haven't said that one yet. And did we get them all? Plus or minus 3 also. Plus or minus 3 over 1, or just plus or minus 3 we could write. Did we get them all? How can you know whether you got them all? How many should there be in this list? Yeah, why do you know there are going to be 6 or actually 12, but whatever. Yeah, there are 3 of these, 2 of these, so, you know, the multiplication principle. So, yeah, so we should have 6 or in this case 12 plus or minus, right? All right, so if you, I think it was pretty clear before, but like let's imagine someone came along and said that 1/5 is a root of this is a new polynomial, right? New problem. What would you say to that person? Wait for me. Yeah.
5 doesn't divide evenly into 3 because it leaves a decimal.
Yeah, 5 does not evenly divide 3, right? Like case closed by the rational root theorem. I know that 1/5 is not a root, for sure. Now, notice how quickly she was able to like defend the castle from 1/5, right? That was awesome. If before, like a minute ago, before you learned the rational root theorem, this is how you would have had to defend the castle. You would have been like, well, I don't know if 1/5 is a root, but I can check. 3 times 1/5 to the 7th. Give me a minute. Plus 4 times 1/5 to the 4th. Give me a second. Find a common denominator. Right. And maybe, and then you would have been like, oh yeah, in the end it's not 0. But I think it's much quicker to apply this theorem if we take it to be true. Now, again, let me just emphasize, if someone comes to me and says 1/5 is a root, I say right away, I say no. If someone comes to me and says 1/3 is a root, I say, maybe. That I need to maybe check. That actually gets through my filter. If someone says to me, like 1 plus root 2 is a root, well, this says nothing about that, right? That's an irrational number, isn't it? So I don't have anything to say about that. I don't know. I mean, I would actually have to, like, if you were a really good friend, I would actually plug in 1 plus a root 2 for you, and I would test it. But you'd have to be a really good friend, because that would be hard to plug in 1 plus root 2.
But you do a crisp high five.
A crisp high five. Oh, well, that's tempting. Let me think about it. Okay. So say something like Crystal said. Any other way you could, what? Like she said, like 5 doesn't divide 3 evenly, right? So that's a good explanation. The other way you could say it too, if you wanted, you could actually write them all out too, right? If you wanted and say, hey, here's the list of rational roots, and yours isn't in that list, so shoo, go away from me. All right. This is on the slide just for the sake of completeness, but like I don't think I need to say it. At this point, I think it's pretty clear that this is true, right? Okay. We've already talked about like end behavior and why that justifies this claim, and the intermediate value theorem, why that might help us explain why this happens too. But it does help me understand the following. If someone has a cubic, I know at least I should be looking for 1 root, right? That's for sure. You shouldn't give up. Okay, next thing just to talk about is, here's one more tool in your tool belt now. Okay, the rational root theorem is kind of a slick little tool that we'll use here. And so is Descartes' rule of signs. And this actually is named for the Descartes that you know and love. What else is he famous for? What?
Descartes.
Yeah, it's not. Yeah, Descartes, I think, is the proper French way to say it. Right. Can you, anyone remember? Like, what about a famous quote of his? Anyone?
I don't know.
It's not on the wall.
I
I don't think I have any Descartes quotes. You should look. There might be one. No, what's his famous quote? someone was going to say it.
Cogito, ergo sum. Sorry.
Yeah, I don't think I have any Descartes quotes up here. But no, from philosophy though.
Isn't it like cogito, ergo?
Which can you translate from Latin?
Therefore I am.
Yeah. I think therefore I am. He's the one who said that. He's also responsible for doing other things inside of philosophy and mathematics and science. So, like for instance, there's something we use all the time that's named after him. What's that? Yeah, the Cartesian coordinate system is named for him. Anyway, so he also gets this to his name. All right, here it is again, a big body of text that you have to process. Okay, ready? Use your best math reading skills to concentrate on that. Read and understand, and then we'll do in a minute. You got a chance to process it. At this stage, you're probably still like, I wrote it down, but I'm not sure what it means. You're still working on the right stuff. By the way, again, feel free to, if that helps you as a note taker, that's completely fine. But remember, you can also find it online. I think I copied it word for word from the book too. So whatever. I mean, there's nothing special about what I've written up here. And the slides are on that online too, or on YouTube. It's special because I gave it to you. Thank you. I mean, for some people, maybe that helps to write it down. I don't know. Okay. Let's just do the first bullet point, and then we'll worry about the second one in a second. Okay. So I have for us, look at that. All right, I just pulled it out of the oven. This one's already pre-made. This one's here's a polynomial in standard form. There it is. And we're going to go through and count the number of variations in sign in standard form, and we literally are going to go left to right looking for sign changes in the coefficients. So, are you ready? Here we go. Okay, here we go. So we don't count this as a sign change because there wasn't a sign, and it just starts negative. But that, yeah, everyone get excited. That's 1.
Yeah.
2.
Yeah.
3. Okay. You made that exciting. Thank you. Okay. So, all right. So that we just counted the number of variations in sign in f of x, and the answer was 3. So that's the number of positive, apparently, because someone told us, Descartes apparently told us, the number of positive real zeros is 3. Or, what does this mean? So I'll write this down. 3 positive real zeros. Or, what does it say? So what do we mean here? 3 or what?
1.
Or 1. And by positive real zeros, we literally mean places where it crosses the x-axis on the positive side of the x-axis, right? So I want you to think hard about why we could be off by 2, or possibly off by 4 if there were, we might say 5 or 3 or 1 or something. Think about why that would happen. This is an interesting question. So 3 or 1 positive real zeros on the right side of the function. And now let's worry about the left side of the function, okay? So I'm going to write up here f of negative x. We're going to try and do the second bullet point now, okay? We're going to try and figure out where this might, how many times this might cross the x-axis over there. Now, over on the negative x-axis. Yeah, what is f of negative x? Here we go. X to the 5th plus 2x to the 4th minus 7x cubed. We're just plugging in negative x plus x squared plus 4x plus 1. Yeah? All right, so now we're going to do the same exact test for f of negative x. And I want you to think...
Isn't it minus 2x?
Maybe, I don't know. No. Okay. This is just plug in negative x everywhere, and if it's to an odd power, that'll change the sign here. If it's to an even power, it will do nothing. So we're going to count changes in the sign here, and also think about why if you take this test to be true, then now we haven't proved that ever, but then why does it make sense that the second one will work? Well, what is f of negative x compared to f? What kind of transformation of the function is that? So if the test worked over here for the positive x-axis, yeah, it's flipped somehow. How? Yeah, over the y-axis. Then now we're just applying the same test again to a new function, and we're using the positive real axis again. So this will tell us about the negative side though. So all right, here we go. Ready? 1, no, 0, no sign changes. You ready? 1, 2, and that's it, right? All right. So what do we say here? How many negative? Yeah, 2 or 0. So it either crosses the negative x-axis 2 times or 0 times over here. Okay. And again, I want you to think about why is there this off by an even number thing happening? You know, I need you to think about that just for fun. Okay. Yeah, Lauren. Yeah. All right. So a thought question for you to think about, like why would we be off by 2 ever? What would be going on there? Notice if we just take these 3 and 2 here right now, at least. Now there are some other footnotes here, but if you have 3 and 2, that adds up to 5. So I don't know. Will that when will that not be true? I'm trying. Yeah. Anyway. Yeah.
I just noticed that when you add a minimum and a maximum, they both equal 3. Like so, one of them was 1 positive and 2 negative. The other was 3 positive and 0 negative.
Yeah, you could have 3 positive zeros and 0 negative real zeros. That would be fine. Yep. It could only have 1 real root, right? Total 2, couldn't it? It's a 5th degree polynomial. It could only have 1 real root. Total. Oh, I like what you're talking about up here. All right, let's do it. Are you ready to do this? I promise this will be our destination. So here we are. Would you like to just have a go at it? No calculator. Give it a try. I'll let you struggle for approximately 4 minutes, and then I'll come alongside. Okay?
You're intentionally letting us struggle.
Yeah. Corrective struggle. That's where the learning happens.
Wait, one step.
Use all the tools you might have in your toolbox.
1 plus 6, that'd be 5. Sorry. And you got negative 12, which would be negative 7. And then now you have to add 12.
I don't really understand
5.
what I'm doing right now. Like,
And you have to subtract 11. Subtract 11 would be, yeah, negative 6. Negative 1 is we could use synthetic division.
You need to find one root that's exciting, right?
X plus 1 is a
It's like you're unlocking a rule that
But oh yeah, I hate it.
Yeah, it can be. If there's no possibility, it's like.
All you do wait, is there no concept?
I want you to factor this through. You know what factor is, right?
There's no sign.
We got one more value.
Oh, it's the time.
X squared 4 plus 5
Oh, wait, is it like, if I
plus
say
7 x squared plus 5x plus 6. Okay, I'm doing a worse. It is no, we still can try negative 1 again. The new equation.
I don't know.
So this is 3 minus 5. No, that doesn't work.
It doesn't matter plus or minus is enough.
Yeah, well, we know it has to be negative, right? So can we try but I know I'm going to give up.
You have to divide 3, so we're talking about either plus or minus 1 or plus or minus 3. The cube should divide this cube. So 1, 2, or 4.
So we're not allowed to use
Zero, I have to be 1.
3 halves.
Sure? Okay, cool. 2 is synthetic.
So there will be
So
one.
Yeah, the denominator needs to be
I'll be right back. We're having so much fun.
There will be
Well, I actually like math, and then like, I like.
It's a bit big a school, only in same
I think that was 4 minutes of struggle. Okay. I'm gonna.
No, that was more time.
We got 2 roots.
You got 2 roots already? Good. All right. You found 3. Oh, good job. It's like an Easter egg hunt. It's so fun. Okay. When you find them, it's exciting and it's better than candy. All right.
It's better than candy.
All right. So what are the possible roots? The possible, I should say, rational roots. I mean, just because that would provide a good starting list to guess from, right? I don't know. Cassie, you have some?
So what are plus or minus 1, plus or minus 6, plus or minus 2, plus or minus 3?
All right, it's kind of nice. It's kind of nice when this leading coefficient is 1, isn't it? It's kind of nice. But then you also realize something else. What's that?
They're all negative.
There's no, in fact, there are no positive roots of this polynomial. It's just not possible. Okay? The sign, think about what Descartes tells you about this f of x. No sign, m of x. No sign changes at all. So I have a pretty short list of nice ones. And if we're in math class and you like know personally the author of the question, you might guess that some of the roots are nice, right? So, and by nice we maybe mean like integer or rational roots. So, all right. So let's try some of these. Again, since we're lazy, we're going to try low numbers first. Yeah? And we've already learned from the warm-up today that in fact, plugging in these numbers is equivalent to actually doing the synthetic division, if you like, right? It's actually maybe easier to do this, actually do the synthetic division. So I'm going to actually set this up here. 1, 6, 12. Are there any zeros needed here? No? Okay, good. Here we go. Does negative 1 work? Hey, look at that. Okay. So again, let's just keep track over on the side here of where we're at in life. M of x equals m plus 1. Didn't we just discover that m plus 1 is a perfect factor? That's what we discovered, since negative 1 is a root. And what do we have left over? We have m to the 4th plus 5m cubed plus 7m squared plus 5m plus 6. Beautiful. And now we have a new task in life. We have this little depressed polynomial to work with. Can we factor it? Okay. Now, the possible roots I think are still the same. So, I don't know. Let's try some of them again. Negative 1 maybe? Does negative 1 work? Negative 1. Well, it doesn't. If negative 1 divides in, it could divide in again, right? It's still a possible root, so I thought I'd test it just for fun. And it's not going to work. Okay, so you're right this time. Have an eraser handy. See, for times like this. Okay. Let's try negative 2. Does negative 2 work? By the way, do you see how isn't this slick? Reuse the, because I'm trying to factor this, and I already have it right here. You see how that's working? Okay. Pro tip. Okay. Hey, look at that. Negative 2 works. So let's keep track of our status. We have m plus 1. That's definitely a factor. We've just realized that m plus 2 is also a factor. Leaving behind m to the 3rd plus 3m squared plus m plus 3. Aren't we making progress? Do you feel how this works? We're chipping away at it. Well, we'd like to factor this as much as possible. Yeah, we'd like to continue factoring if there's a root. And we know there are roots of that. Cubic, it's a cubic. It has to have at least one root. So we don't need to ever test negative 1. By the way, negative 1 is out now, isn't it? Right? Because I tested it a second time and it didn't work. Right? So it's certainly not going to be a root of this guy because it wasn't a root of this guy. What else is out? What else is out? Look at this polynomial down here. Think about rational roots and stuff, right? I think negative 6 is out, isn't it? That can't be a rational root of that guy anymore. What else? Negative 2 is also out. So maybe negative 3 works, right? So you could try that again over here. Or maybe you just know how to factor that too, though. Do you? I think you know how to factor that. Maybe you factor by group or something? Alright, homework 3 tonight. Quiz is going to be on Thursday, which is a little different than the calendar says, so I apologize for that.